We're now going to take the same idea and we're going to imagine a kind of thought experiment where we're going to put sodium and chloride in one compartment and just water in the other compartment, and imagine how the sodium ions and chloride ions can move from one compartment to the next. So let's go up here, take this panel, and describe this as ion movements. We're going to call this diffusion across a barrier. We'll take the same pattern. There's a beaker. But now, in the middle of this beaker, we're going to put an imaginary wall. This is simply a barrier. On this side of the barrier, we're going to put 1 liter of water. And then on the other side of the barrier, at precisely the same volume, we're going to have water plus 100 millimolar sodium ions and 100 millimolar chloride ions. So basically, we've just taken the story we had up above in that single compartment. We've now separated that into 2 compartments. On the right-hand side is 1 liter of pure water. On the left-hand side is a sodium chloride solution, which is 100 millimolar sodium chloride. Now, of course, if this is a brick wall, the sodium ions, as they're bouncing around, and the chloride ions, as they're bouncing around through thermal agitation, through random movement, will bounce against the wall and bounce off. They're not going through. It's an impervious wall. But let's say now that we can put selective holes in this wall so that we can put chloride selective channels or holes, and we can put sodium selective channels or holes. Now, if you only have 1 or 2 sodium holes, 1 or 2 chloride holes, it's going to take forever for one of these ions to find that tiny hole and find its way through. If given an infinite amount of time, they'll find the hole and move through. But let's make this a little easier. Let's put thousands and thousands, maybe even millions of holes in the barrier. And now imagine the chloride ions and the sodium ions bouncing against the wall. They bounce against the wall, and now and again there's an opportunistic hit. It's just a lucky hit where it hits the hole just right and goes through. So now this sodium ion, and similarly down here, the chloride ion, has moved from one compartment to the other, simply by random chance of finding a hole and moving through. Now recognize at the initial stages of this, where we have only sodium chloride on the left-hand side and none on the right-hand side, that the probabilities are absolutely such that sodium and chloride moves from the left chamber to the right chamber, moving from regions of higher concentration to regions of lower concentration, simply through the random walk, the Brownian motion of those ions. But now, given time, the sodium and the chloride move from left to right. And over time, the concentration of sodium and the chloride in the left-hand compartment go from 100 millimolar down to 50 millimolar. And during that same period of time, the concentration of sodium ions and chloride ions on the right-hand side go from 0 millimolar to 50 millimolar sodium and 50 millimolar chloride. So basically, we start out with everybody on this side, but through this random walk, we end up with 50 millimolar sodium on this side and 50 millimolar chloride on this side. But we also have over here 50 millimolar chloride and 50 millimolar sodium. We are truly at equilibrium. We have the same concentrations on both sides, and we reach that equilibrium simply by allowing the sodium and chloride to move from their higher to lower concentration. Once you've reached the equilibrium where there are the same number of sodium and chlorides on the left side as on the right side, the probability of a sodium ion bouncing against the wall and going right to left is the same as the probability of bouncing against the wall and going left to right. And that's true for the chloride as well. We have reached an equilibrium where the probability of moving from one chamber to the other or the other to the one is exactly the same. That's an equilibrium. We're going to see this kind of movement of ions through a random walk over and over again, and it really lies at the heart of generating electrical potentials in muscle and in nerve, and we'll really come back to this several times. But again, it's just the random walk. That's all we're talking about. We use the randomness of sodium and chloride moving from one chamber to the other to reach a new equilibrium.